Today we're going to be looking at section 5.6 and talking about link layer switches and virtual LANs. Okay, as we build up to this, we're going to talk about ways that you can interconnect link layer devices. The most simple of which is called a hub, and these are really hardly ever used anymore because they're so dumb and bad in terms of performance. Hubs are just physical layer devices. That means they're dumb repeaters. They hear a signal coming in and they repeat it out on every other line. Right? So this is the hub in the middle. Right? It receives signals and it sends them out as it gets them. It doesn't buffer a frame. It doesn't accept a whole frame and then send it out. It just repeats what it hears. There's no frame buffering. There's no CSMA CD. There's no protocol that's going to listen before it sends. Remember all that? Carrier sense multiple access. So because of that, it's very possible that it could create collisions among all the other nodes. Really, all of the nodes on this network connected by a hub are in the same collision domain. All right? They all have to listen to each other, and the hub is just allowing them to talk to each other in a bigger way. So those are hubs. They're just physical layer 1 devices. This is bad. We can do better than this. That's what a switch is. A switch is an improvement. It's a link layer device. It's smarter because it understands the link layer and it's going to implement the link layer protocol, the link layer rules. It actually will store and forward Ethernet frames. So it's going to accept a whole Ethernet frame and then send out a whole Ethernet frame and not just rebroadcast what it hears. Secondly, it will selectively forward packets or frames. What that means is it will look at the frame's MAC address and selectively forward the frame to one or more outgoing links that destination should be on. Lastly, the switch uses CSMA CD, so it uses carrier sense multiple access with collision detection when it's talking. So that means it is going to listen first, and when it detects a collision, it will stop. Switches are nice because they're transparent. The hosts themselves don't have to know that the switches are there. You can just plug it in. It's plug and play. It learns the topology of the network by listening and broadcasting packets to figure out what MAC address is on what port, so they can only have to send packets to the port that's necessary. In this sense, in this case, hosts have dedicated direct connection with the switch. The switch is buffering packets. The Ethernet protocol is used on each incoming link, but collisions don't happen because each link is its own collision domain. What that means is that collisions aren't going to happen because the switch is going to make sure that they don't happen. If A is trying to talk to A prime, you can hardly see my primes, and B is talking to B prime, C is talking to C prime, all three of those can basically go on simultaneously without any collisions happening because the switch itself is doing the store and forwarding, and it's forwarding packets from one incoming link to an outgoing link without there actually being an interference between the two frames. How does the switch know how to do this switching? How does it learn by itself? All right. So we can see by looking at this, because we can see the whole picture, that A prime is on 4 and A is on 1. How does the switch learn this? All right, the switch has a switch table, and that switch table holds the MAC address, the interface, that is the outgoing link for that interface, and it has a timestamp, which will be used for time to live, kind of an expiration, a timeout. How are entries created and maintained in this switch table? Creating the switch table is the important part, and once we have a switch table created, we can just look up in the switch table, hey, where is this destination address, this destination MAC address, in this case letters, and when we figure out which link it's on, which are our numbers, we'll just send packets, just send frames addressed to that MAC address on that link. So this switch table is a little bit like a routing table in that it's just looking up how to forward incoming packets to outgoing links. But it's all based on link layer addresses, and it's just within this nodes connected to this. Well, that's not exactly true. We can connect switches together and they still work. All right, so this slide kind of explains how if we have a packet that looks like this, that is we have a frame, it's from A and it's intended to go to A prime, right, and it has some payload. When the switch receives this packet from A prime, it'll receive it on number 1. Then it immediately knows, hey, if I have a source packet that's A and it's on link, and I received it on link 1, then I know what link MAC address A is on. It's on 1. Yeah? So it's learned that. How is it going to find out where this frame goes between 2, 3, 4, 5, and 6 when it doesn't know? Initially, this is the only thing that's in the table. All it knows is that A is on 1.
The return?
Well, the return just has the MAC address, and the switch has to know, all right, which port or which outgoing link is A prime on. So if we don't know where somebody is, what are we going to have to do?
Broadcast the signal.
Right, broadcast it to everybody else. All right, we do that, so we're going to send this frame down to 6, 5, 4, 3, and 2. The way the Ethernet works, every host are going to listen, or really the network interface card is going to listen, and if it receives a packet that is addressed to its address, it's going to pick it up. If the frame is not addressed to it, it's going to ignore it. Okay? So everybody else is going to hear that broadcast address and ignore it, except for A prime, because it is destined for A prime. All right, so in response to that, A prime is going to send back a packet to the switch from A prime to A. Most likely, right, if we're in any kind of bidirectional communication. When this happens, the switch will learn, okay, well, A prime is on number 4. So the next time I need to send something to A prime, I'm just going to send it out on link number 4, and I don't have to send it to everybody else. That make sense? So by overhearing these conversations, it'll learn, and as long as this time to live is not expired, it's not down to 0 yet, then we can continue using that. We would have to erase this entry from the table when this time to live is up.
Does it reset every time it's used?
I expect it would be, yeah. So what this allows for, if the network changes, right, if you switch 2 around, then it needs to be able to adapt to that. But as long as things aren't changing, then the table's still correct. So to kind of sum this up, if the destination is unknown, we flood the packet, we broadcast it. If the destination is known, then we can selectively send, and that's much more efficient, right? We don't even have to waste everybody else's time listening, time and bandwidth, listening to packets that aren't addressed to them. This is sort of a pseudocode description of how this switch filtering and forwarding happens. That we're going to record the link associated with the sending host. In our case, we remembered A was on 1. We will look in the switch table for the MAC address. If the entry is, if the destination address is in our table, then we, if the destination is on the segment from which the frame arrived, we drop the frame. So it may be that there are actually 2 computers on that same link that are talking to each other, and that switch doesn't need to be involved. It doesn't need to forward it to any of the computers on the other links. If the destination is in the table on a different interface, then we forward the frame to that interface. If it's not in the table at all, that's what this else block is for, then we will flood it or broadcast it. And that means we're going to forward it on all interfaces except the one that it arrived on. All right, so let's take this up to the next level. What if we have multiple switches connected to each other? What if, in this case, we've got 4 switches, 1, 2, 3, and 4, and we've got these hosts A through G. What happens if A needs to talk to G? How does switch 1 know to forward the frame sorry, this is explaining A to F. So if we need to go to F, how do we need to go? Need to know to go through S4 down to S2 and then into F. I think this is wrong. This should say G. Okay, so this is the good news in this case. Because of this property of self-learning, this actually works the same as in the single switch case. We can imagine if, basically, if we don't have it in our table, then we're going to broadcast it, and when we broadcast it, we're going to broadcast it to some other switches, right? And if they have that frame in their table, they'll send it to the right interface. If they have that destination in their table, their switch table, they'll send it to the right interface, which might be another switch, or it might be the actual host. So if it doesn't know it, then it'll broadcast it, right? And then everybody will get it. And eventually the right person will get the broadcast packet. And when they respond, then everybody else will learn the reverse mapping. Yeah? Okay. So we can connect multiple switches together and have a network that has multiple switches, and we still get this nice effect where we've really reduced the number of collisions. Does that make sense why we're reducing collisions? Because now really only one person can talk at a time. We're going to learn where everybody is, and we're just going to send it out on the link that host actually is on. So now our institutional networks are actually going to look a little bit more complicated. They might look something like this, where we have switches connecting the kind of the local area networks to each other, even within this whole institution, and we can just have one router at the edge of the institution network that's actually doing routing. Everybody in here can do switching, and switching is relatively efficient, right? So in this case, this network wouldn't have to run routing protocols to figure out where things should go, because really there's not but just a few options anyway, and the switch will learn that. It won't require that many broadcasts to figure it out. So let's compare switches and routers. We talked about routers in the last chapter, and we just talked about switches here. They're both store and forward devices, meaning they accept the whole packet and then they resend it. The big difference here is that routers are network layer devices. They understand the network layer, they understand IP, whereas switches are just link layer devices, so they just understand about MAC addresses. They're not going to ever process the data that is involved in an IP address and those kind of routing decisions. A router uses a routing table, whereas a switch uses a switch table. There's some similarities between there, but we see how the creation of routing tables is different. How do we create routing tables?
Extras.
By running routing algorithms like Dijkstra's, right? How do we create the switch table? Right, through this algorithm we just described, algorithm protocol, this self-learning mechanism, right? Just by kind of overhearing and by broadcasting. So that's kind of the difference between how the table is created, routing algorithms versus this filtering, learning algorithms. Okay. So that is routers versus switches. Any questions on that? Okay. The second topic in this chapter is about VLANs. You guys heard of VLANs? It stands for Virtual Local Area Networks. Here's the idea. If you could imagine, from the way we've looked at it, it would seem that, well, let's just look at this scenario first. Let's imagine that we've got this university, and they've got a computer science and electrical engineering and computer engineering department. People who work in those departments connect to the switches for those departments. And that's the way this network is structured. Well, what happens if a CS person moves offices over to electrical engineering, to that other building, but they still want to connect to the CS switch for whatever reason? It's important that they're on that network. Well, as we've seen before, this would be, we'd have to have a different switch, and we'd have to, if you had moved physically over here, you couldn't physically connect to this switch anymore. You'd have to connect to the electrical engineering switch. This administratively is not good. The network administrators want more control over the structure than this. So what has been implemented is a virtual network where we can actually have different virtual local area networks that exist using the same physical switch. And I think this explains it pretty well. So in physically, there's one switch. But virtually, we look at it as if there were two different switches, and some of the ports are associated with one virtual network, and other ports are associated with the other network. Does this picture make sense? I feel like it explains it better than I could in a lot of words. So one physical switch, multiple virtual switches. So if the computer guy moves to the electrical engineering building, all we have to do is make sure that we just have to reconfigure the switch to say, okay, well, port 9 is now in the or maybe port 7 here is actually yellow. It's in the computer science virtual network. Yeah. So the switch makers build in these capabilities so that you can define multiple virtual LANs over a single physical LAN infrastructure. This makes it just a lot easier. I guess an implication from this, a result, is that we can actually isolate traffic. So we can make sure that the traffic that's on the blue switch, the electrical engineering switch, can only, those frames could only reach ports 1 through 8. So this is nice. We've separated the traffic that doesn't probably need to go to each other anyway. How do you forward between virtual LANs? You could do it with routing, just like with separate switches. In practice, vendors sell devices that are switches and routers, so it takes care of everything right in there. Oh, as I said here, because we're using VLANs, we can have dynamic membership, which means that the ports are dynamically assigned to whatever VLAN we want them to be in. Like I said, we've changed this to yellow. And the routing and the forwarding is done. The forwarding is done through routing. You can see here, we've got this router that's external here. You can imagine if the router is built in, the routing software basically is built into this same hardware, then it can do it all in one box. Additionally, it's even possible to have VLANs that span multiple switches. So even though we've got multiple physical switches that map onto different different virtual networks, in order to do that, you do have to be able to define how these things are connected to each other. They call this the trunk port that connects one physical switch to another physical switch. But all the blue ports are one virtual LAN. All the yellow ones are another virtual LAN. And this 802.1q VLAN frame format defines how this could be implemented. All right, so the main takeaway from this is that we can create multiple virtual networks within a physical network infrastructure that's actually different. And these kinds of capabilities ease the system administration, maintenance. They improve flexibility for networks. Any questions on this idea?